Hello again. So now I'm going to do this problem, okay? So let's read it together. Suppose that a 35-foot tree's shadow at a particular moment of the day is 7 feet. Suppose that you observe your shadow at that moment is 1.5 foot. 1.5 feet. How tall are you? Okay. Now, of course, if I'm asked how tall I am, I know you can't tell it, from looking at the camera, but I'm 1,000,000 feet tall. Okay? No, I'm just kidding. But now we have to get serious and we have to look at this problem. Okay? Let me begin by drawing a figure. So this is my sun over here that's like emanating light, of course. Right? We can put a smiley face on it if we want. Okay? This is the ground over here. Okay? This is my tree right here. Okay? Okay. Okay, that's my tree. And we can suppose that the shadow that it leaves, let's say it's like this. Okay, this shadow has length 7 feet. Okay. And then at the same time of the day, and let's suppose that at a similar location, let's say I'm over here, for example. This drawing doesn't really capture it, but let's say this is me here. Okay. And here I am, I'm wearing a monocle, as I usually do. And I have a hat on. And let's suppose that I'm also leaving a shadow, but my shadow is 1.5 feet. Okay? Like this. Now, I want to point out that the assumption here is that the angle that the light is hitting these two objects, the tree and the person, is roughly the same. Okay? That you're in close enough proximity that we can imagine that the angle of the sun is hitting the same. So this would be like a more realistic picture. Okay? Okay, so this is more a realistic picture, and now what we're going to do is we're going to make a schematic, okay? These triangles essentially will overall basically kind of overlap, like this. Okay, this angle, this angle will be the same for both figures, okay? This height is the height of the person, 1.5. This height is the height of the tree, which is 35. We know that the shadow, not the height of the person. The shadow of the person is 1.5. And since we know that the shadow of the tree is 7, in the schematic we can say that this is 7 feet, okay? And then what we don't know is this part here of the triangle. And so our assumption also is that this is a right angle in both, because you assume that the person is standing up straight and that the tree is also standing up straight. And then of course, if you have this angle the same in the larger triangle as in the smaller triangle, and you have these two angles being a right angle, and since the sum of the angles in a triangle is 180, then this angle must be the same as this angle, right? Because in this smaller triangle, 90 plus this angle will equal some value, right? But 90 plus this angle will equal the same value. So if you take 180 minus that value in this triangle, you're going to get some value that is the same as this value will be when you take 180 minus the sum of those two, because again, as we said, these two add up to the same value as these two. Okay? Okay. So there's a result from geometry, and it basically says that if you have two triangles, and if the corresponding angles of the two triangles are equal, then the triangles are similar. Okay? And I'm gonna discuss what that is right now and what it will tell us that will help us solve this problem. And so now we're going to need this fact for this problem, and that is that these two triangles are basically they're similar. Okay, so what does that mean? Triangle ABC is said to be similar to triangle DEF, which is denoted triangle ABC with this squiggly line, triangle DEF, if and only if the length of the segment of AB divided by the length of the segment DE is equal to the length of the segment AC divided by the length of the segment DF, and if that is equal to the length of the segment BC divided by the length of EF. Okay? Now, basically what this means is that the side lengths of one triangle are a multiple of another. Now, I don't mean a whole number multiple. They could be a whole number multiple. Like if I were to take the length AB and double it for DE, and I did the same for BC, like in other words, EF being twice BC and DF being twice AC, then the two triangles would be similar. But it's not necessary that they be whole number multiples. Okay. The basic fact, though, is that what similarity captures is that the figure has been dilated by the same amount. Each side of the figure has been dilated by the same amount. I defined here similarity in terms of triangles, but you could say that two pentagons are similar if the side lengths were stretched by the same amount. Okay, for example. Now, okay, I didn't notate it there, but as I mentioned verbally, our argument for as to why these two triangles are similar was that they have the same angle. So in other words, if you look here at the triangle formed by the tree, okay, and the ray of light that goes like that to form the shadow, this angle was the same as that angle here. This angle, which is right, is the same angle there, and this angle at the top is the same as the angle there. Okay, and in other words, what I'm saying is that for two triangles whose corresponding angles are equal, the triangles are similar. Now, if the lengths are the same, then the triangles will be congruent. But in this case, that's not the case because the person is going to be, in this case, shorter than the tree. Okay, that's not a given. It could be that the tree is a sapling, right? But here we can tell the shadow of the tree is larger, so we can imagine that the height of the tree is going to be bigger. Okay, so but how do we get the exact value? Let me show you that here. So I'm going to label this schematic drawing of our situation like this. I'm going to call this angle A, this point B, A, then this point B, which is the upper part of the small triangle, then C, D, and I'm going to call this E, E being this point right here. Okay? So from this schematic, what I'm claiming is that the triangle ABE is similar to the triangle ACD. Okay? Okay. Now, one of the things I also want you to notice about the way I notated the similarity from our schematic is I matched up the location of each of the angles. So if you notice, the location of A is the location where they both have the same angle, this one. The location of the B and the C is where they both have that same angle. And the location of the E and the D is where they both have the same corresponding angle. In other words, when I stated here the relationship of the similarity, I'm doing the same thing, okay? For example, here in the notation that triangle ABC is similar to the triangle DEF, the angle at A and the angle at D are the same, okay? The angle at B and the angle at E are also the same, okay? And then the angle at C and the angle at F are the same, okay? For the similarity notation. In other words, that notation captures, it summarizes more information than it just looks like automatically. Okay? But now with that said, we can translate this into a relationship, a relationship that we will then be able to translate into an algebraic equation, which we'll then be able to solve. So now here, I can say, okay, AB divided by AC is going to equal to AE divided by AD, and the BE divided by CD. Okay? So what I've just written here is the proportional relationship among the sides of these triangles, of these two similar triangles. So now I'm going to fill in what I know, okay? I know, first of all, in this case, for our problem, we don't care what AB is, but I'm just going to notate that anyway. So it's AB. We don't know anything more about it, so I'm just going to leave it as AB. The AC, I'm just going to leave it as AC. The AE, aha. The AE, which is the shadow of the person, is 1.5. The AD is the shadow of the tree. That's going to be 7. That's going to equal to BE. That's the height of the person that we don't know. And, of course, we've labeled that as X. So what is X? X is the height of the person. Okay? Okay. And then finally, our CD is going to be the 35. Okay. Okay. And so now we're going to be able, with this relationship that we just wrote down, we're going to be able to solve this problem. So now, what I want you to observe, and this is going to come in handy right now as we're going to try to solve this problem, is the following relationship that you should commit to memory. If you have the fraction AB equal to the fraction, A over B equal to the fraction C over D, then the product of A and D will be equal to the product of B and C. Okay? Okay. Let me show you how that's going to play a role here. If you notice here, this part doesn't give us anything, but here, this relationship gives us everything we're going to need to solve this problem. Okay? So let me copy that part over here. 1.5 divided by 7 is equal to X over 35. Okay? So now from this rule, okay, which I want you guys to commit to memory, you know that this is going to be 1.5 times 35 equal to X times 7, which we'll write as 7x. Okay? Okay. So now what I can do here, okay, let me erase this over here a little bit so I can give myself some room, okay, to do the multiplication of 1.5 and 35. Okay, so I have 35 times 1.5. Okay, I ask myself, what is 5 times 5? That's 25, right? So I bring my 5 down and I carry the 2. 5 times 3, 5, 10, 15, 16, 17. Okay. Then I ask myself, what is 1 times 5? It's 5. Notice how I put the 5 underneath the 1. What's 1 times 3? 3. Okay. Now I add them. So 5 plus 0 is 5. 7 plus 5 is 12. I carry the 1. 1 plus 1 is 2. Plus 3 is 5. And because I have one decimal among all the factors, I move it once to give me 52.5. So I can see that 52.5 is equal to 7x. Now, to get the x by itself, to find the height of this person, okay, I'm going to divide both sides by 7. This is going to be divided by 7. This is going to be divided by 7. So I'm going to be left with x equals, the height of this person is going to be 52.5 divided by 7. Now, of course, we don't want to denote the height of the person like this, with a number like this, right? So what we're going to do is we're going to carry out the long division. Now, of course, you can use a calculator here if you want, and I encourage you to do so if you feel that that is appropriate at any given moment. But if you want to, you can also do it by hand. You ask yourself, does 7 go into 5? It does not. Does 7 go into 52? In fact, it does, right? It goes 7 times. Why does it go 7 times? Because 7 times 7 is 49. So 7 times 7 is 49. I put that here, and I subtract. What is 2 minus 9? I cannot subtract 9 from 2. So I borrow from here. This becomes a 4, and this becomes a 12. 12 minus 9 is 3. 4 minus 4 is 0. Okay. Then I bring down my 5. Okay. There's a decimal point here, so I put my decimal point there. 7 goes into 35 5 times. 5 times 7 is 35, so that's 35. I subtract and I get 0. So I can see that my person is 7.5 feet tall. And I know it's feet because the height of my tree was given in feet. Okay? One of the things that I would want you to take away from this problem is to recall the definition of similarity. If you want, you can put that on an index card to be one of the facts that you want to know. Another thing I would want you to take away from this problem is how I set up and labeled the schematic diagram, because that helps us solve the problem. I want you to notice how I identified the similarity relationship, and then I wrote down my ratios just looking at, just the way I wrote it down in my definition. The more internalized you have these definitions, the more formulaic and automatically and more effectively you'll be able to use them. And of course, it doesn't hurt to draw a little cartoon diagram first, just to try and see what's happening in the problem, especially in a geometric problem like this. And I want you to also notice how we set up the algebraic equation, how we recalled this fact, and then how we solved it and identified the unknown value to solve the problem. I hope you've enjoyed this, and thank you, and I'll see you soon.